Hello and welcome to today's lesson. In this first tutorial, we are going to look at the introduction to graphing tangent and cotangent functions and begin to look at the domain and range. So we are in the first half of section 5.5 in your textbook. We're just going to be focusing on the tangent and cotangent functions in this section. The tangent is equal to the sine divided by the cosine. That might help us to figure out some of these tangent values. We're going to do the same thing that we did with cosine and sine functions and look at certain key points. I'm going to look at these angles, 0 pi. I'm also going to look at all the pi over 4s in the middle. Pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and back to 2 pi. I'm going to look at the tangent value for each one of these angles. I'm going to make a big t-table and figure out the tangent value for each one of these. So 0 pi, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. Just made it. Okay. So since the tangent is the sine divided by the cosine, I can take each one of these. You know what? I'm going to list these ordered pairs. 1, 0, 0, 1, negative 1, 0, and 0, negative 1. If we're looking for the tangent value, the sine divided by the cosine, I can take the y-coordinate 0 divided by the x-coordinate 1. 0 divided by 1, of course, is 0. So at 0 pi, the tangent is 0. When I get to pi over 4, I remember that that's the 1 in the middle, the angle that's in the middle, but I call it the 1 in the middle because tangent will be 1. It's the same cosine and the same sine, so when I divide them, I get 1. When I get to pi over 2, though, I get my sine value divided by my cosine value will be undefined. I'm going to put the null set symbol. The tangent does not exist at pi over 2. The 1 in the middle here, but this time it will be negative because the cosine is a negative value. Pi, the tangent is 0 for the same reason why it's 0 here. 5 pi over 4 is the 1 in the middle. This time we're back to positive 1 because now it's a negative divided by a negative. The same situation at 3 pi over 2 that we had at 1 pi over 2. The tangent does not exist because we cannot divide by 0. 7 pi over 4 is the 1 in the middle, but this time again it's negative because the sine is negative while the cosine is still positive, and back to 0. Okay, so let's graph this. It's going to be our normal label, so 1, 2, 3, 4, I'll put my pi, and 8 tick marks over, I'll put my 2 pi. 4 tick marks to the left, I'll put negative pi. I'll go up 2 tick marks to make a 1, and down 2 tick marks to make a negative 1. I'm going to graph my tangent in red, so I'm just going to graph from my t-table. When I go to 0 pi, my output is 0, so there's my first point. When I go to pi over 4, I get a 1, so that's 1 tick mark, and I get a 1. Now when I get to pi over 2, I get undefined values. So I'm going to put a vertical asymptote. Our tangent function does not exist at pi over 2, so I put a vertical asymptote. Let's keep going. 3 pi over 4, that would be 3 tick marks over, and my output is negative 1. When I get to pi, my tangent value is 0. When I get to 5 pi over 4, that's 5 tick marks over, I'm back to 1. And when I get to 3 pi over 2, again we have an undefined value, so that will be another vertical asymptote. We do not exist right there. Keep going, 7 pi over 4, the 7th tick mark, we have a negative 1 output. And 2 pi, we are at 0. So those are all of the outputs from our unit circle values, but this pattern can continue. I know that my next tick mark is going to have a 1, and my next tick mark is going to have a vertical asymptote. I'm going to continue this pattern so we can see much of the tangent function. My next tick mark, I'll be back to -1, and my next tick mark, I'll be at 0. I'll stop over here, but I will come back here and continue the pattern backwards. This is a 1 and then a 0, so this must be a -1. And then we have a vertical asymptote. And then we're back to a 1 and a 0 and a -1, and our final vertical asymptote. So these are all the points here, at least from -3 pi over 2 to +3 pi. And I'm going to start putting in each of the tangent curves. And these are curves. So I will connect them like that. They all are identical. Now, of course, I'm graphing a whole lot more than we will be graphing with each one. I will just be asking you to graph a single period of the tangent curve and the cotangent curve. I'll just stop right there. But for right now, I wanted you to see at least, well, let's see, 4.5 periods of the tangent curve. Now, because there's only one period that we want to be graphing, let me bold in the very first period of the tangent function. Let's bold this in or identify it somehow. This is actually the first period of the tangent function, and this is the one that we would be graphing. So I'll make that a little bit bolder for everybody to see. Bold that in a little bit more, and those are our dots. Now let's talk about domain and range. The domain for the tangent function, we actually have infinite restrictions because we have infinite asymptotes. So how we're going to describe the domain for the tangent function, it's going to be the set of all x such that x is not equal to, now we have to list infinite asymptotes. Well, I'm not going to sit here forever listing every single one, so I'm going to show you how to do it efficiently. I need the first asymptote. Now what I do is I pick the closest asymptote to 0, to the origin. Now I actually have two asymptotes that are exactly equidistant. So in this case I pick the one that's positive. The first positive value where our domain does not exist, or our tangent does not exist, is at pi over 2. So x cannot be equal to pi over 2. And if you notice, all of the asymptotes are exactly the same distance away from each other. They are all 4 tick marks away from each other. And 4 tick marks is represented by pi. So if I add a multiple of pi to my pi over 2, I have a list of all of my asymptotes. The first one is pi over 2, and the next one is pi units away. And the next one is pi units away from that, and so on and so forth, or negative pi units away if I'm going in the negative direction. So k is just representing an integer like I showed you in a previous tutorial. This is how we can define all infinite asymptotes. And we'll practice that when we do our graphs. Range, well, the range is pretty simple. We go from negative infinity to positive infinity, so that's just all reals. You can write the set of all reals, or you can say negative infinity to positive infinity. Now let's look at our cotangent. The cotangent is basically the reciprocal of the tangent, and that's how I'm going to find all of the points in my cotangent. If you'd rather see it as the cosine divided by the sine, and look at the unit circle values all the way over here, that's fine. I'm just going to use the idea of reciprocal. Let's put my labels in first. Fourth tick mark is pi, eighth tick mark is 2 pi. Alrighty. Having a little trouble over here. Okay, and the fourth tick mark over here is negative pi. I'll just put that in there. And I'll go up 1 and down to -1. Okay, and I'm going to do this graph in blue. So I'm taking all of the reciprocals of the tangent values, and I'm just going to start here at the origin. Right here I've got 0, and the reciprocal of 0 is 1 over 0. But 1 over 0 is undefined, which means that I have a vertical asymptote right at the beginning, right down that y-axis. When I go to my next value, I'm at 1. With the reciprocal of 1, well, the reciprocal of 1 is just 1. So I'm fine with just a 1 being right there. And then I get to this asymptote. Now, the reason why we had an asymptote right here is because we were dividing by 0. If I take the reciprocal of that, then that must put the 0 in the numerator, which is good. 0 can be in the numerator. We get the value of 0. So every place where we have a 0 in the tangent graph, the reciprocal is going to be an asymptote. And every place we have an asymptote in the tangent graph, the reciprocal is going to be a 0. So now we can put in all the asymptotes. They were at pi, or the zeros if at the tangent, or will be the asymptote, so it's at negative pi, so that's going to be a vertical asymptote. We already did the one at 0. Pi, there's a vertical asymptote. 2 pi, there's going to be a vertical asymptote. And one more 0 from the tangent, the reciprocal of that will be another vertical asymptote. That's at 3 pi. All of the places where we had a vertical asymptote at pi over 2 and 3 pi over 2 and 5 pi over 2 all become zeros, and those are exactly in the middle of our asymptotes, so I can put those in. The reciprocal of 1 is just 1, so each one of these places where we have a 1 is still 1, so that's right here and right here. The reciprocal of 1 is still just 1. And the reciprocal of negative 1 is just negative 1. 1 over negative 1 is still negative 1. So that's here, 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 and here. And now we have enough points, hopefully, to see what our cotangent curves look like. Oops, I forgot this part. They all look exactly the same. And again, I'm graphing more than I actually need, because I really just want you to graph one period of it. I just wanted to show you all that I could on this graph patch. I'm going to graph the very first period. I'm going to darken it in or make it a little bit wider, thicker. That's the first period of the cotangent curve. Notice, of course, that it looks like it's the reciprocal of these graphs, but there's also a kind of a shift because the vertical asymptotes are at different locations as well. Now let's talk about domain. Same type of domain, we have infinite restrictions. So we're going to say all x such that x is not equal to, again, I like to find the first restriction. And the first restriction is actually right here at 0. X cannot be equal to 0 pi. And then how often after that do the asymptotes repeat? They repeat every pi units, every 4 tick marks. So instead of saying 0 plus pi k, I can just simply put pi k. Remember, k is just an integer, so k can represent 0 or 1 or negative 1, and we have all of the restrictions right there. The range is all reals. One last note I'd like to make on this page is what the period for the tangent and cotangent graphs are. Again, the period is how often it takes for the graph to repeat itself. If you recall, for sine and cosine, the period was 2 pi, but now when you're looking at either one of these graphs, you can see that it takes exactly pi units before the graph starts to repeat its values again. If you haven't noticed yet on your unit circle, all of your tangent values from the first quadrant, you don't need to go all the way back around to get to them. You can just go halfway around and see the same exact tangent values, exactly 180 degrees or exactly pi units away. The period for the tangent graph and the cotangent graph is 1 pi. So we have a different period for the tangent and the cotangent graphs. I have one little note about amplitude on my next slide. Okay, I lied. It looks like it's a very big note. There is no amplitude. when we're talking about the tangent curve or the cotangent curve, it doesn't make sense to talk about amplitude. Amplitude is a height, and as you can clearly see from either one of these graphs, they are already infinitely tall because the range is all reals. So we do not call an amplitude for the height. There still is a value of a, and it's still in the same exact location. We just simply do not call it amplitude. Okay, so the method that I use to graph tangents and cotangents is a little bit different than we did for sines and cosines. What I like to do is simply find the vertical asymptotes. And the only part of the function that's going to change the vertical asymptotes is right here, the bx minus c part, basically the thing in the parenthesis. What we're going to do for the tangent curve is set bx minus c equal to negative pi over 2, and we're going to set it equal to positive pi over 2. We choose positive and negative pi over 2 because these are the original asymptotes for the tangent graph. We're going to solve this equation for x, and we're going to get the new vertical asymptotes, whatever the equations solved for x will be. And then I'll show you what to do then. So we're going to set bx minus c equal to these two original asymptotes, solve the equation, and we'll find the new vertical asymptotes. And then I'll tell you what to do. So for cotangent, it's very similar, but it's a cotangent graph. So bx minus c is going to now be equal to 0 pi and equal to 1 pi. Those are the two original asymptotes for the cotangent graph. Again, we're going to solve for x, and we're going to get the two values that x now equal for the two new vertical asymptotes. That's how I like to graph them, or at least how to start them. I'll show you on the examples how to do that. If you want to find all of your other information like we have before, it's still the same exact stuff. Amplitude, though, does not exist for tangent and cotangent. They're already infinitely tall, so it doesn't make sense to talk about its height. But the horizontal shift is still going to be c over b, and the vertical shift is still going to be the value of d. The period, remember, it's your normal period divided by b, and in this case, our normal period is 1 pi for tangent and cotangent. So you can still find this information if you really need. That's the end of this first tutorial, which is the introduction to the graphs, and we'll look at 4 examples in our next tutorial. Thanks for watching. Yeah, thank you. See ya.